So let's go ahead and check the answers here. Now you may have gotten these in a different order. So for this one here, we have sodium phosphate. We'd like to know how this is classified. And as a class, this is a strong electrolyte. Now, we have a number of you that got this one wrong, either saying a weak or a non-electrolyte. I mean, if you're a non-electrolyte, you're in big trouble. Honestly, you're in big trouble right now. How would you identify this as being electrolyte?
Ionic.
It's an ionic compound. And it is aqueous. If it's an aqueous ionic compound, it is a strong electrolyte. Okay, any questions on that one? Okay, next one. Which of the following is a weak acid? Select all the choices that apply. H2CO3. Again, if you picked B, you're in trouble. If you pick D, you're in trouble. If you pick E, you're in trouble. Okay, I can see maybe if you get A and C mixed up, but how do we, first of all, identify something as an acid? Hydrogen's out front, exactly. So if you're thinking that any of these others are acids at this point, honestly, you're in big trouble today. You better be studying. And I'm not just saying this to be mean or a jerk or anything, but you're in trouble if you can't tell that these things are acids. Then there was a list of acids that you were to memorize. We talked about weak acids and strong acids. Of course, the ones you should really focus on memorizing is the strong. And if you know the 6 strong acids, any other acid you encounter is going to be a weak acid. Okay? Next up, which of the following is a strong base? Get on your list to memorize. We did a little better on this one. Hydroxides make this one here a strong base. It has to be a group 1A or group 2A hydroxide. Then it was HNO3 reacts with water. When dissolved in water, select both of the products of this reaction. So you had to give 2 answers on this one. Hydronium ions and nitrate ions. Hydronium ions are produced because, how do we classify HNO3? It says an acid. All acids, when dissolved in water, produce hydronium ions. And so then if you kind of do the math here and figure it out, if we have hydronium ions, basically this hydrogen goes over and attaches itself to H2O. That leaves us the nitrate ion over here as the one that is left over. And finally, KNO3 goes through which process in aqueous solution? And that would be B. It goes through dissociation. And why does this go through dissociation?
Aqueous.
Well, it's aqueous, it's true. But remember, what does dissociate mean? To separate or to come apart. So what type of compound is potassium nitrate? It's an ionic compound. So if you put an ionic compound in solution, it's simply going to dissociate or separate into its constituent ions. And actually all of these here today, I've put down all 5 of them because these are all very central to what we are going to be doing today. And what we're doing today is going to be very central to the lab that you are doing next week and actually on the exam. Today we're going through completing and balancing chemical equations. And you've done that before if you had a previous chemistry class. What many of you probably haven't done before, I know in our 1020 when we teach here, we don't talk about net ionic equations. So the net ionic equation piece is going to be new to most of you in here. And in order for us to understand net ionic equations, you have to be able to tell what is a strong electrolyte, what is a weak electrolyte. And then you should be able to distinguish between your strong acids, weak acids, strong bases, and weak bases. So all of these here that we put up here today are going to be pretty central to what we're covering for today and then what's in your lab and exam next week. So that said, any questions on any of the 5 coming here into class today? All right. So what we're going to do then is this. First of all, here's what you're going to be responsible here for in this class when it comes to completing and balancing chemical equations. Completing and balancing chemical equations. And we talk about completing and balancing, what we mean is that if you were given the reactants, you should be able to figure out what the products are. And also for today, you need to pull out the handout from Tuesday, the half sheet. Anybody not get the half sheet here on Tuesday? Two of you there. Pass this down. Two of you here. Three of you here. Give me a break. All these guys did not get this on Tuesday. Anybody else? All right, let's get it out. All right. The types of reactions we're responsible for completing and balancing are double replacement reactions, which are sometimes also called double displacement. And the other type you will be responsible for completing and balancing will be combustion reactions. And we're going to start today with double replacement reactions. Now, in a double replacement reaction, we have a setup like this. We have AB plus CD, where AB and CD represent ionic compounds. And what happens then is that the positive ions trade places. And positive ions trade places. So when they trade places, what would we have for products? C, B, and AD as the possible products. And so again, the positive ions trade places in these reactions. And I'm going to start here with a demonstration. In fact, I have several that we're going to demonstrate here today. And we're going to start with this reaction. I have a couple substances. They are calcium chloride, and the other one is sodium carbonate. So calcium chloride and sodium carbonate. And we'll go ahead and put these out here. Here's my sodium carbonate. Put that in. And we'll put in our calcium chloride. First thing you ought to notice here is that ionic compounds come as solids. So if you're seeing this and it clearly isn't a solid, what phase would it be in? This is not a liquid. Aqueous solution, exactly. So if we know that the compounds come as solids, as ionic compounds, if we see them and it looks like a liquid, then we should know that they are dissolved in water. So you can label each one of these as being aqueous solution. We go ahead and mix them together and watch what happens here now. Pour one in the other, and I believe we've talked about these before. This is the formation of a precipitate. We call this a precipitate. Have we not used that term in here? No? Okay, well, now we're using it. This is called a precipitate. And the word precipitate means literally to fall out. The word precipitate means to fall out. So, of course, if you hear the word precipitation in everyday language, we're talking about what? Rain, which of course is falling out of the sky. So in this case here, when we form a precipitate, what will happen is that this precipitate is going to fall out of a solution. Eventually, this will settle to the bottom. So a precipitate is a solid that forms when we mix together two aqueous solutions. So again, this is called a precipitate. So now, if we want to write out a chemical equation for what just happened, we need to remember how double replacement works. Calcium had been paired with chloride, but now if it trades places, calcium will be paired with which stuff? Carbonate, and sodium would be paired with chloride. So again, it goes through that double replacement, and then we could go ahead and write out a chemical equation that shows what just happened. We started with calcium chloride, so it's going to be CaCl2, and some of you, in fact probably most of you, will need to get your periodic table out. I do have some periodic tables. You can never have too many. Anybody need a clean, fresh periodic table? That's another one down here. Anybody else?
Like my fourth one. I'm just too lazy to get it out.
Anybody else? Remember, you can never have too many. All right. So, if you got killed on nomenclature before, you're going to get killed even worse when it comes to chemical equations. So, come back here and we look at it. Calcium is Ca with a charge of 2 plus. Chloride is Cl with a charge of 1 minus. We have a 2 positive charge on the calcium, a single negative on the chloride. So the formula becomes CaCl2. The phase label we put down for calcium chloride would be aqueous, right? Because it's dissolved in water. Next, it's reacted with sodium carbonate. Sodium is Na with a charge of 1 plus. Carbonate, CO3 with a charge of 2 minus. Now if you've forgotten these, again, you're going to have to go back and review them. So the formula for sodium carbonate would be Na2CO3. Phase label is aqueous once again. So then we did our double replacement. Calcium now paired up with the carbonate. So once calcium paired up with the carbonate, we have 2 plus and a 2 minus. The formula of calcium carbonate is CaCO3. Let's not worry about phase label quite yet. And then the other product is sodium chloride. Charge on sodium is 1 plus, chloride is 1 minus. So the formula of sodium chloride is NaCl. Okay. Now, good question is, what happened to the 2's? Or where do the 2's go? It's going to go in front. We cannot write the formulas like this, because if we write the subscripts down below, we're creating formulas of something that doesn't exist. Okay? So what we want to do is we want to balance this chemical equation like we've learned thus far. And we put a 2 here in front of the NaCl to balance the sodiums and to balance the chlorines. Are the calciums balanced?
Yep.
Yes. Are the carbons balanced? Yes. And are the oxygens balanced? Yes, they are. We do have a balanced chemical equation, but we're still missing phase labels. So with the phase labels, this is where we use our solubility tables. These help tell us what phases we find for the products. Now the way that you read this is that the top portion represents soluble compounds, the bottom portion represents insoluble compounds. And so you read these down, basically whatever appears under the category, and then you look for exceptions. So in the case of calcium carbonate, we want to figure out its solubility. So we come back here and we see that carbonates are at the bottom. They are under the category of insoluble. And then we look for some exceptions. Is calcium carbonate an exception?
Nope.
No, it's not. So since it is insoluble, what is a phase label for something that is insoluble? Solid, right. Remember, S doesn't stand for soluble, S stands for solid. And then if we look up sodium chloride, we find sodium ions right up here. If a compound contains a sodium ion, it is soluble with no exceptions. But soluble with no exceptions, we can go ahead right away and phase label would be aqueous. So again, if it's soluble, it's aqueous. If it's insoluble, it is solid. So then that takes us back to our beaker here. Now we're in lab, and we want to figure out what's in here. We know then that there's calcium carbonate and sodium chloride in here. What if we want to get the calcium carbonate out of here? What would we do with it? Well, look carefully. What could we do to get the calcium carbonate out? We could filter it, right. We need to filter this. And if we filtered it, where would we find the calcium carbonate? In the filter, the stuff that goes through. In the filter, exactly. So, and this is the way that chemists make things. If you want to know, you come back to our stockroom and look that we have shelves all over with chemicals all over the place in there. If you want to know how we make chemicals, it's not like you just dig up, well actually calcium carbonate you kind of dig up out of the ground. But a lot of the chemicals that we have there is not something you just dig out of the ground. You have to make them by reacting the proper things together. And so in the case of calcium carbonate, if we wanted to make this, we could make it quite easily by reacting together something that contains calcium ions, something that contains carbonate ions, and make the precipitate and filter that stuff out. So any questions on the demo? Okay, now this equation right here is what we call a molecular equation. And it's kind of a misnomer. By misnomer, a misnomer is something where what you see doesn't really match what it really is, because we're calling it a molecular equation even though how many of these things are molecular compounds? None of them. Okay, so this is a place where chemists have bad vocabulary, and you can get by with bad vocab on this one because that's what chemists call it. All right, but what we're going to do here is we are going to now go from the molecular equation to what we call the ionic equation. And this is where students start running into trouble, is when we go from the molecular to the ionic equation. When we go from the molecular to the ionic, what we're going to do is we are going to separate all of the strong electrolytes. All of the strong electrolytes get separated into their constituent ions. So again, all of the strong electrolytes get separated into their constituent ions. And just as a quick review, what constitutes a strong electrolyte? They are your aqueous ionic compounds and your strong acids. They're aqueous ionic compounds and your strong acids. You might say, well, shouldn't strong bases be up here too? And the answer to that question is strong bases already are up here, because all of your strong bases are aqueous ionic compounds. So all of your strong bases are already ionic compounds to begin with. So since acids are not ionic compounds, we must also specify them as well. So what I recommend doing then is going through the chemical equation and asking yourself on each one, and that's why we started with this here today. On each one, say, is this a strong electrolyte or not? So we'll start with the calcium chloride. Is this a strong electrolyte? Well, it's aqueous. Is this an ionic compound? How the hell do we know? How do we know? Metal and nonmetal. If it's an ionic compound, we have metals combined with nonmetals. So is this a strong electrolyte? Yes. All right, we go to the next one. We have sodium carbonate. Is this a strong electrolyte? Yes, because the ions that make it up are sodium ions and carbonate ions. Okay, and is it aqueous? Yes, it is. So this is a strong electrolyte. Is the calcium carbonate a strong electrolyte? And why not? It's not aqueous. It is an ionic compound, but it is not aqueous. So this one here is not a strong electrolyte. Is calcium chloride a strong electrolyte? Yes, because it's aqueous and it is ionic. So as long as it's a ionic compound that is aqueous, it is a strong electrolyte. So now, for each one of these here that we labeled as a strong electrolyte, we're going to separate them into its constituent ions. And again, this is where if you didn't learn your nomenclature before, this is going to kill you here, and you're going to have to go back and practice your nomenclature if you want success with these. And I hate putting it that way, but I have to be more honest with you guys because you're the ones that want to be the doctors and the pharmacists and the engineers. You guys got to get this stuff down. All right? So, calcium ions have a formula of Ca with a charge of 2 plus. Chloride. How many chloride ions are in this formula? 2 of them. So we would show that there's 2 chloride ions. Sodium carbonate is made up of which ions? Sodium ions and carbonate ions. Sodium ions have a charge of 1 plus. Carbonate ions have a charge of?
You can't forget the 2.
Yeah, I can't forget the 2, right? Thank you. I'm going to put my coefficients in color so you can see them. Yep. How many carbonate ions do we have? We have 1. If you look at the formula, there's just 1 carbonate ion in the formula. But there's 2 sodium ions in here. We put a 2 in front of the chloride because we have 2 chloride ions in this formula. And the formula of the chloride ion is not, so this is where I'll see some people writing it wrong, it's not Cl2, the minus charge. Chloride ions are Cl with a single negative charge, so if you have 2 of them, you want to put that 2 out front. And then we're going to show the products. The products of this reaction are calcium carbonate, and that doesn't get separated because we're only separating the strong electrolytes. So anything that's not a strong electrolyte stays intact. And then we have sodium chloride. How many sodium ions are we showing? 2 of them. And how many chloride ions are there? 2 chloride ions as well. So we put in a 2 here, we put in a 2 here. Again, that's because if we have 2 moles of sodium chloride, that means we have 2 moles of sodium ions and 2 moles of the chloride ions. This is what we call the ionic equation. And before we go on, I need to know if there's any questions on how we come up with the ionic equation. Any questions on this? Now is the time to ask. Not 10 minutes from now when we're doing another example. Any questions? All right. Now, if this is an algebraic equation, you would think of this arrow as an equal sign. If you think of this as an equal sign, you're seeing some stuff on the left-hand side that's the same as the stuff on the right-hand side. And if it's an algebraic equation, they have stuff that's both the same on each side, what do you do?
Cancel the respective lines.
Cancel them out. So what is common to each side? 2 chloride ions and 2 sodium ions, exactly. And then what we have left over looks like this. We're showing calcium ions combined with carbonate ions to yield calcium carbonate solid. And this is what we call the net ionic equation. This is the net ionic equation. And the net ionic equation is what we wind up with. Net ionic equation is what we wind up with when we cancel out the ions common to each side. And the ions that we cancel out that are common to each side are what we call spectators, or spectator ions. We'd say in this case that the spectator ions are the sodium ions and the chloride ions. Okay? Spectator ions are the sodium ions and the chloride ions. Now here's what this all means. Here's what all of this means. First of all, the net ionic equation is the actual reaction that happened in here. So the net ionic equation represents the actual chemical reaction that took place. And the actual chemical reaction that took place in here is that calcium ions hooked up with carbonate ions and formed calcium carbonate. That's the actual reaction that took place in here. The spectator ions, now if you're at a football game, who are the spectators? They're the ones in the stands. They're basically just watching what's happening. And that's exactly what the sodium ions and chloride ions do. They're watching what happens. They're supporting the reaction. And by supporting it, what we mean is that, well, if we wanted to get calcium ions to react, you just can't go into the lab or anywhere in the world and find calcium ions. Calcium ions don't come by themselves. Calcium ions, which are positive ions, have to be paired up with negative ions. And likewise, you're not going to go anywhere in the lab and find carbonate. Carbonate is a negative ion. So if we're going to find carbonate somewhere, carbonate's going to come paired up with a positive ion. All right? So if I go back to the shelf, I would have to, if I wanted to make calcium carbonate, I would have to find something that contains calcium. It wouldn't have had to have been calcium chloride. That's what I used here. It could have been calcium nitrate. It could have been calcium bromide. It could have been all sorts of stuff. The carbonate didn't have to be sodium carbonate. It could have been potassium carbonate or lithium carbonate. Basically anything that could have gotten the reacting ions into solution. So again, the technical term is, we'd say that the spectator ions don't actually participate in the reaction. Just like you're at a football game, the spectators don't actually participate. However, once again, we need the spectator ions there to bring the reacting ions into solution. So again, the spectators are there to bring the reacting ions into solution. So any questions that you have on our intro here to net ionic? Which, that is what we're doing today, is net ionic equations all day. But we're looking at a bunch of variations. So any questions on this one? All right, next up, let's do this one. I have some iron 3 hydroxide. You can write down the names just like we did before. I suggest stacking the names like I did before. Iron 3, not hydroxide, it's iron 3 what? Chloride. Sorry, it's iron 3 chloride. And I'm going to react this with what? Sodium hydroxide. Put this back up here. And if you look now at this one that we did earlier, you should be able to see, if I bring this up to light, you should be able to see how the solid is beginning to settle to the bottom in here. So we talk about the word precipitate. The word precipitate again means to fall out. And so that's what the solid here is doing in the solution. It's falling out of solution. Eventually this will all settle to the bottom, and we could recover it that way instead of filtration. Okay, so let's go ahead and do this one. I'll put some iron 3 chloride into this beaker. And then I'm going to take some sodium hydroxide and put it into this one. And then I'll go ahead and pour one into the other, and we'll watch what happens when we do this here. we get a nice precipitate once again. What does this look like, by the way, inside here? Crap?
Yeah.
Yeah. Well, it also looks like rust, okay? So this is what wet rust is. So what you're looking at is wet rust. But let's see what the formula is for a wet rust. We take the iron 3 now. Iron 3 is now going to hook up with which ion? Hydroxide. Sodium will hook up with chloride. So now we go ahead and write out the chemical equation. We'll start with the iron 3 chloride. Iron 3 would be Fe with the charge of 3 plus. Chloride is Cl1 minus. So the formula for iron 3 chloride would be Fe Cl3. Phase was aqueous. Remember, if it's an ionic compound that looks like a liquid, that means its phase is aqueous. Always. Okay, then we combine this with sodium hydroxide. Sodium is Na with the charge of 1 plus. Hydroxide, this is the one that you had to memorize. It is OH negative. Formula for sodium hydroxide is NaOH. Phase label is aqueous. Right? Okay? Remember, it came aqueous. It came out of this bottle right here. So now, if we want to figure out the products, we've done that already. Products are iron 3 chloride. So iron is Fe with a 3 plus charge. So how do we write this formula? Parentheses and the 3 down below there. 3 for a subscript. And then the other product would be NaCl. That's because we have Na with a plus charge, chloride with a single negative charge. Now to figure out phase labels, we go back to our solubility table. We're going to try to figure out the solubility of iron 3 hydroxide. Find hydroxides here which are insoluble. We then look for iron 3 as an exception over here. We don't see it, so that means that the phase label on iron 3 would be, or the iron 3 hydroxide is solid. We shouldn't need to look this one up because we already done it. It's aqueous. And what's another reason why we wouldn't have to look it up? What is this stuff? Salt. And what is salt? Ionic compound, right. That's this stuff here. Can we dissolve this in water? Yeah. So you shouldn't even have to look this up right here. And the other thing you shouldn't have to do or wind up doing is sometimes I see that these subscripts carry over and they say NaCl3. Well, what the heck is that? That's not this stuff. This is NaCl. If you write NaCl3, I have no idea what you're writing. Okay? So make sure that you know your formulas. Okay, then we balance the chemical equation. What do we need to balance it? The coefficient here would be 1. How about in front of the NaOH? 3. How about in front of the iron 3 hydroxide? 1 in front of here? 3. Okay? This here is your balanced chemical equation. What do we call this equation as it's written? This is your molecular equation. This is your molecular equation. Now we are going to write out the ionic equation. If we write out the ionic equation, we need to identify the strong electrolytes. So we then go back and ask yourself, is iron 3 chloride a strong electrolyte? Yes, it is. Aqueous ionic compound. So yes, it is a strong electrolyte. Is sodium hydroxide a strong electrolyte? Yes, it is an aqueous ionic compound. Is iron 3 hydroxide a strong electrolyte?
No.
No. And is sodium chloride a strong electrolyte?
Yep.
Yes, it is. In fact, that's one of them that we proved the other day was a strong electrolyte when we tested it in here. Okay, so now, from here, we're going to write out the ionic equation. So the ones that get separated are the strong electrolytes. So let's separate all of the strong electrolytes into their constituent ions. How many iron ions do we have? How many do we have? 1. How many chloride ions do we have?
3.
3. And we write the chloride ion as Cl with a charge of?
1 minus.
1 minus. And we got 3 of those chloride ions. How many sodium ions are there?
3.
Again? How many sodiums are there? There's 3. How many hydroxides are there?
3.
It's 3 as well. If we have 3 sodium hydroxides, we have 3 sodium ions. We have 3 hydroxide ions. And then these react to yield. What do we do with the iron 3 hydroxide?
Keep the same.
Leave it alone. Don't touch it. And then sodium chloride. How many sodium ions here?
3 and 8 plus 1 plus
3 sodium ions and
1 plus
how many chloride ions?
3.
3 of them as well. So now that we have our ionic equation written out, we can go from here to the net ionic equation. To go to the net ionic equation, what do we need to do?
Get rid of the spectator ions.
Get rid of the spectators. So chlorides goes away. What else goes away?
Sodium.
Sodium ions goes away. And then what we're left with is the net ionic equation. And that net ionic equation shows that iron 3 ions react with what else? Hydroxide ions. How many hydroxide ions? 3 of them. And this yields iron 3 hydroxide. And that's the solid. Now ordinarily we don't write down what the spectator ions are, but if the question was what are the spectator ions in this reaction, they would have been sodium ions and chloride ions. And if we were to write them out, you would show them that they are sodium ions and chloride ions. Now the biggest trouble that students have with this in the past is that I usually see this. I'll see the charges absent. And if the charges are absent, this implies something very different than Fe with a 3 plus charge. This is implying that we have like a solid metal dissolved in aqueous solution, and that doesn't happen. Okay? You have ions that are present in aqueous solution, but a metal itself, if we were to drop in iron into water, it's not going to dissolve or anything else. So we want to make sure that when we're showing these net ionic equations, that we show the ions where appropriate. Now, let's say that instead of sodium hydroxide, I'd used potassium hydroxide. In other words, this would have been KOH. What would have changed in the net ionic equation? Nothing would have changed. Why? Right, because then the potassium ions would have become spectator ions. We would have still wound up with the same reaction overall. It's just that if I didn't have sodium hydroxide available, maybe I would have had potassium hydroxide available and could have then used it in the reaction instead. So the spectator ions are important. They do bring the reacting ions into solution, but they themselves do not participate in the actual chemical reaction. Any questions on this one here? And I know you think you're getting this down. So let's try this one. I'm going to take some potassium iodide, and I'm going to mix it with some sodium carbonate. Sodium carbonate. And let's see here, make sure I get the correct stuff out. Put that one away. So sodium carbonate. Here's the sodium carbonate. And then I have some potassium iodide in here. And of course, ionic compounds are solids, so if we see them looking like this, that means that they are aqueous. Not liquids, but aqueous. All right. So now we take these two and we mix them together and watch to see what happens. One of the things you notice is, what happened? Nothing. Okay, there's no reaction that took place. Now this is one that we could have predicted that no reaction took place. And it works something like this. First of all, let's write out how we'd represent that in no reaction. We come back to the periodic table. What is the charge on the potassium? 1 plus. Iodide, here's
1 minus.
1 minus. Iodide is right here. So again, it'd be 1 minus. Sodium is Na with the charge of
1 plus.
1 plus. Carbonate is
2 minus.
CO3 with a charge of 2 minus. So the way that you would write this would be like this. You'd have Ki, aqueous, reacting with Na2, CO3, aqueous. And then after the arrow, we'd write Nr. Is usually the way that chemists write it. Nr stands for no reaction. But here's how we could have predicted it. First of all, let's say that we had written products down. If we had written products down, they would have been potassium carbonate and sodium iodide. In other words, if we wrote them out here, I'm going to try to stick these together a bit more. So it would have been potassium carbonate. Potassium carbonate is K2CO3, and sodium iodide would be NaI. Then if we went and looked up the phase labels, we come back and we see that potassium carbonate is soluble, because if it contains potassium ions, it is soluble with no exceptions. Okay? You say, well, wait a minute. Carbonate down here says it is insoluble, but if you read the exceptions, it says when it pairs up with potassium, it is going to be soluble. So both ways it is confirming that potassium carbonate would be a soluble compound, which we label as AQ. And of course, because this contains sodium, this would also be aqueous as well. And so the rule works something like this. If you start with 2 aqueous ionic compounds, and the products show that 2 aqueous ionic compounds would form, then there will be no reaction. Okay, so again, if we start with 2 aqueous ionic compounds, and the products show the 2 aqueous ionic compounds would form, then what we have is no reaction. You can't even write the products down when they don't react. If you wrote them down, you'd be writing them down incorrectly, because there's not a reaction that took place. We verified that no reaction took place, so you can't write a reaction for a reaction that doesn't take place. Okay, but the way you predict it is if you start with 2 aqueous ionic compounds, products show 2 aqueous ionic compounds form, it's no reaction. Now we can also show this. Now this part you don't need to write down. I can write this a lot faster than you. Okay, so don't write this down. Just follow along on this. I'm going to balance this real quick, assuming that they had reacted. If they had reacted, this would have been a 2 and a 2. And so now I would have gone through, I would have identified this is a strong electrolyte, strong electrolyte, strong electrolyte, strong electrolyte. Maybe you see where this is going. If I write the ionic equation, which ones do I separate? All of them. So I have 2 potassiums, 2 iodide ions. I have 2 sodium ions. I've got carbonate ions. Yielding 2 potassium ions. I have carbonate ions. I have 2 sodium ions, and I have 2 iodide ions. What happens? They all cancel, exactly. They're all spectators, and because they're all spectators, that's telling us that nothing took place. And that's exactly what we observed, is that nothing took place. So if you wind up doing that yourself, this would be the long way to discover there's no reaction. Okay, but it is another way that you could confirm that there's no reaction that took place. And so the correct answer for this one would have been this piece right here. Any questions on this one? Okay, let's do some stuff here with acids and bases. We're going to take some hydrochloric acid. Hydrochloric acid. And we are going to react it with some sodium carbonate. Not sodium carbonate, I think sodium hydroxide for this one, sorry. Sodium hydroxide for this run. Well, now we want to go ahead and check out what happens in this case. I'm going to put the explosion screen up for this one. This is not explosion screen this time, it's a splash screen, just so Mohammed and you guys don't get splashed with anything. So we take, where's my hydrochloric? Here's the hydrochloric. I'll put some in here. I'll go ahead and put some sodium hydroxide in the other one. And what I'm going to do to make this one a little interesting is I'm going to measure some temperatures. So we'll go ahead and, I think I opened up Logger Pro, here we go. And we'll measure the temps, which you can see in the lower left-hand corner. I don't remember which one this was. I think this was the HCl. This is the first one I put in. Yeah, we'll click collect in just a moment. I'm just getting the initial temps. It looks like we have about 24 degrees on this one. And if we go to the sodium hydroxide, looks like we have the same temperature, about 24 degrees. So what I'm going to do now is I'm going to go ahead and put this into motion, and I'm going to go ahead and pour one into the other, and watch what happens here now when I pour. And of course, how does it feel now in my hand? Pretty warm. And of course, if you looked at this one, simply by looking, you may have guessed that what had happened. Probably no reaction, because you would have looked at it and seen nothing happened. But if you were holding this, you would have felt that it was getting warmer. And we've evidenced that by measuring the increase here in temperature. So sometimes, and to be fair, we didn't do that with this previous one. Okay, so what I should have probably done on this previous one that we saw no reaction, so we should have measured its temperature. If we would have measured the temperature in this one, we would have seen nothing happen. But sometimes when we see nothing happen, it might be that we can't see anything happening, but we can feel something happening. And so in this case here, I can definitely tell you that the temperature in this one is going up. So that means that a reaction has occurred. So if a reaction has occurred, then we should be able to write out a chemical equation for this reaction. So let's go ahead and do that. Now hydrochloric acid is going to have a formula of HCl. And if you've forgotten your nomenclature, remember that a hydro prefix with an IC acid suffix tells us that this is a binary acid. This is a binary acid. So the hydro prefix tells us it's a binary acid. And so if it's hydrochloric, that means you have hydrogen with a single plus charge. Chloride is Cl with a single negative charge. Sodium hydroxide has a formula of NaOH. And that, of course, is because sodium is Na with a charge of +1. And hydroxide is OH with a charge of 1-. Okay, so we go ahead and put these two down. Aqueous and aqueous. And now we have to do a double replacement. So if we do a double replacement, sodium is now going to hook up with chloride. So these will hook up, and hydrogen ions will hook up with hydroxide ions. Okay, so sodium hooks up with chloride, we get NaCl. Phase label is going to be aqueous, as of course this is salt. What do we get when we put H plus with OH negative?
H2O.
H2O. That's HOH. Phase label of water is liquid, not aqueous. Okay. It's aqueous when we dissolve it in water. If it is water, it is a liquid. Unless it's really hot or really cold, then we have a different phase. So now we need to balance this equation. Is this equation balanced? Yes, it is. Yeah. 2 hydrogens on each side, 1 chlorine on each side, 1 sodium on each side. So now let's go from here, and we're going to write out the ionic equation. So in the ionic equation, we want to separate all strong electrolytes into their constituent ions. Is hydrochloric acid a strong electrolyte? Ooh, what are those strong electrolytes again? They include aqueous ionic compounds and strong acids. So we come back. Is hydrochloric acid a strong electrolyte? Yes, because it is a strong acid. Is sodium hydroxide a strong electrolyte?
Yes.
Yes, it is. Is sodium chloride a strong electrolyte? Is water a strong electrolyte? Okay. So now that we've identified them, we're going to write out the write out the ionic equation. So to write out the ionic equation, we take all of these strong electrolytes and separate them into their constituent ions. So hydrochloric acid, I know we just finished talking about acids last class period. We would have talked about it containing hydronium ions and chloride ions. However, we are going to write them as hydrogen ions and chloride ions. And the reason for that is because chemists sometimes like to take shortcuts. And we showed in here in our last class period that a hydrogen ion by itself is not going to be stable. If a hydrogen ion is by itself, its charge is super concentrated. And because its charge is super concentrated, it's going to seek out something else that is negatively charged. In the case, it's going to seek out water molecules that have pairs of electrons. So we'll just know that when we write it down. And by knowing that, what we mean is that whenever you write down an aqueous hydrogen ion, what you really mean is a hydronium ion, but you're just too lazy to write it. Okay? That's what it boils down to. So when you write hydrogen ions, and that's what chemists do, we know when we see a hydrogen ion that's aqueous, that it's not really a hydrogen ion, that it's really a hydronium ion, but we're just too lazy to write it. Okay, we don't want to mess around with extra work associated with that. Sodium hydroxide consists of sodium ions and hydroxide ions. Sodium chloride consists of sodium ions and chloride ions. And water consists of water. Right. Water is a molecular compound, so we don't separate it. So at this point then, what we do, get rid of the spectators. So the spectators in this case are chloride and sodium ions. And so what we're left with then is the net ionic equation. And the net ionic equation would show hydrogen ions react with hydroxide ions to yield H2O, liquid. And what's interesting to note here is this. First of all, we note the net ionic equation. This net ionic equation is the net ionic equation that we would get whenever we react together a strong acid with a strong base. So again, this is the net ionic equation that we would get in all cases when we react together a strong acid with a strong base. And the reason why we say that is if we go back and look at the examples, let's say that instead of using hydrochloric acid, we use nitric acid, which is a strong acid. So nitric acid is HNO3. So if this would have been HNO3, this would have been sodium. And if this was nitric acid, what would this product have been? Sodium nitrate. But we would have still had two strong electrolytes. You would have then had nitrate ions here and nitrate ions here. They still would have canceled out. If we had used lithium hydroxide instead of sodium hydroxide, lithium ions then would have been the ions here that canceled out. We still would have gotten the same net ionic equation. So always when we react together a strong acid and a strong base, we are always going to get this net ionic equation. And as far as the molecular equation goes, and this is probably something you learned in high school, if you react together an acid and a base, your products are always going to be a salt plus water. When you react together an acid and a base, your products are always going to be a salt plus water. Now, most of you up this stage, you think of salt as this stuff. This isn't the only salt there is. This is what we call table salt. Okay? But when a chemist uses the word salt, we're basically referring to any inorganic ionic compound. So any ionic compound pretty much would classify as a salt. And so chemists use the word salt not just for this stuff that we may consume as a part of our diet, but we use it for any ionic compound. And so they'll generally follow this model. Now, one exception that doesn't follow this model when we react together an acid and a base is if the base is ammonia. And so we're going to look at that next one. What happens if that base is ammonia? So the next reaction we're going to look at is what happens when we take hydrochloric acid and react it with ammonia. Actually, I don't think I can do this one here, demo it, because I don't think I brought out the ammonia. That's all right. We'll just talk about the reaction then. Had I done this one, we would have seen the temperature go up, just like we did with this reaction right here, because this is an acid, this is a base. And when acid and base get together, they are exothermic reactions. They get warm, just like we observed the one get warm right here. But now, for this particular one, when ammonia is the base, we wind up forming an ammonium salt. So again, when ammonia is the base, the salt that forms is an ammonium salt. And so if we think of this as being an ammonium salt, what is the name of that ammonium salt going to be? Well, what is the ammonium ion? NH4 with a charge of? Man, we got to review this really bad, don't we? It's NH4 with a charge of? 1 plus. So if we have NH4 with a charge of 1 plus, what is the name of the salt going to be if we put these together? Ammonium chloride. It's going to be ammonium chloride. There's not any other elements in there. It's going to be ammonium chloride. So we put it together here, and ammonium chloride is the salt that we wind up getting. Now, if we had, unfortunately I don't have it out here right now, but ammonia used to formerly be called ammonium hydroxide. And don't write this part down right now, but it used to be called ammonium hydroxide. And when it used to be called ammonium hydroxide, we would then have our traditional formation of products. We'd see very clearly that the ammonium ion would hook up with the chloride ion, and then we'd have water left over. But what chemists have found is this, is that if we try to take some ammonium hydroxide, which we think is an ionic compound, if we try to isolate this compound, we can't. Okay? And we can't do it because if we think of the normal ways, like we heard earlier, if we want to get something out, maybe we heat it up or evaporate it away. If we try to take an aqueous solution of ammonium hydroxide and evaporate and try to somehow recover ammonium hydroxide, we can't do it. And that's because what ammonium hydroxide really is ammonia dissolved in water. Okay, what it really is ammonia dissolved in water. And if you ever find yourself writing a formula for ammonium hydroxide, right away you should get rid of ammonium hydroxide and replace it with ammonia and H2O, because that's really what ammonium hydroxide is. So because there's no hydroxide in it, there's no water that winds up forming, and the product we wind up with is a single product. It's an ammonium salt. And of course, ammonium salts, if we were to look this up, we find out that all ammonium compounds are soluble with no exceptions. And at this point then, if we wanted to write out the ionic equation, we could. So if we write out the ionic equation, we then ask ourselves which of these is strong electrolytes. Is HCl a strong electrolyte? Yes, it is. Is ammonia a strong electrolyte? It's a weak electrolyte. Very good. It's a weak electrolyte. Not a strong electrolyte. It's a weak electrolyte. It's a weak base. Is ammonium chloride a strong electrolyte? Yes, it is. Because what type of compound is this? Ionic, and it is aqueous. So now that we have these, we should be able to write out the ionic equation. Hydrochloric acid is written as H plus and Cl negative. Ammonia is written as ammonia. And ammonium chloride is written as ammonium ions and what else? Chloride ions. Because again, an ionic compound, ions simply dissociate to yielding ammonium ions and chloride ions. So now we cancel out what's common to each side. What's common to each side in this case? Chloride is, right? And so then the net ionic equation for this one looks like this. We say that hydrogen ions combine with ammonia to yield the ammonium ions. And the spectator ions in this case would have been chloride. Chloride ions are the spectators. Okay, any questions on any of what we've done? We got one more here for today, but any of them that we left on these? On your exams, you will get this, yes. In part because there's so many exceptions. Okay, so yeah, this will appear at the top. And this will not be on your ACS standardized final, however. So if I'm going to be a student that memorizes things, what I would memorize for sure are the ones that have no exceptions. Okay, I would memorize for sure the ones that have no exceptions, but this will be with your exam. But again, come ACS final time, it will not be there. So if I'm memorizing anything, I'm memorizing the ones with no exceptions. So basically all your group 1A compounds, so your lithium, sodium, potassium, rubidium, cesium, those are always soluble. Then your nitrates are always soluble, your acetates are always soluble. Okay, last one here for today. We're going to take, I took all that stuff out, and I suppose that's sitting in the back, so I can't do this one here either, can I? Well, shoot. Nothing there. Okay, well I can't show this one. Well, we can write out a chemical equation. You're going to do some of these in lab next week anyhow. So we'll pretend this is one you're doing in lab. That might actually be one you're doing in lab. We took some hydrochloric acid. Hey, wait, I think I got some back here. What I'm looking for is chalk, and I took all my chalk off my cart the other day. And that's what I get for taking it all off my cart. All right, so we take hydrochloric acid and react it with calcium carbonate solid. And I guess we'll have to imagine this. If I drop the chalk into hydrochloric acid, what will happen is bubbles will start forming. It'll begin bubbling. So now we want to handle this as a double replacement reaction. To handle it as a double replacement, hydrogen is going to hook up with which stuff?
Carbonate.
Carbonate. And calcium is going to hook up with?
Chloride.
Chloride. All right. So let's start with the calcium chloride. I'm kind of partial to putting the ionic compounds first. So calcium hooks up with chloride. Formula of calcium chloride is going to be CaCl2. Then if we have hydrogen hooking up with carbonate ions, we're going to get H2CO3. And that's of course because hydrogen has a charge of 1 plus, carbonate is CO3 with a charge of 2 minus. Now, if you ever see H2CO3, you're going to replace H2CO3 with H2O and CO2. So again, if you ever see H2CO3, which by the way is carbonic acid is going to immediately decompose to yield water and carbon dioxide. Likewise, if you ever find yourself writing a formula of NH4OH, you'll immediately replace this with, we did this one already, ammonia and water. If you ever find yourself writing a formula for this stuff, which is sulfuric acid, get rid of this and replace it with water and sulfur dioxide, yes. And if you ever find yourself writing this one, H2S, Actually, leave this one alone. You write it as H2S. This is a gas. So this is one of those few things where this is actually gas, but this is your gas, this is your gas, this is your gas, this is your gas right here. Okay? And I think in lab next week you're going to generate, I think, SO2. I can't remember if you generate hydrogen sulfide or not, but you'll get a chance to generate these in lab next week. And by the way, your lab next week is going to be super, super central to your exam. I mean, you're going to get some practice on the stuff here with your Master in Chemistry, but you will want to complete your lab report before your exam on Thursday, because a lot of the stuff we'll see on Thursday's exam is going to be repetition on net ionic equations and such. Okay? So, we come back here then, we have H2CO3. We're going to replace H2CO3 with H2O and CO2. The gas in this case is carbon dioxide. Water would be liquid. Calcium chloride. Well, it's a chloride. Is calcium chloride an exception? No, it's not. So its phase label is aqueous. So now what we're going to do is we are going to identify all of our strong electrolytes. So if we identify our strong electrolytes, and I'm trying to get these all out of the way so we get all on one line. Is hydrochloric acid a strong electrolyte? Yes, it is. Oh, did we forget to do something? Forgot to balance. Right. We better balance. What do we need to do to balance? Right, there we go. We put a 2 in front of there, and I think that takes care of it. So now, let's identify our strong electrolytes. Is HCl a strong electrolyte? Yes. Is calcium carbonate a strong electrolyte? No. Calcium chloride a strong electrolyte? Is water a strong electrolyte? Carbon dioxide a strong electrolyte? No. Now see, this will be pretty fast. So you want to get the ionic equation. Hydrochloric acid is going to consist of hydrogen ions and chloride ions. How many of each?
2.
2. Good. Then we react this with calcium carbonate. What do we do with the calcium carbonate?
Break apart.
Leave it alone, right? How about the calcium chloride? Consists of 1 calcium and 2 chloride ions. And then what do we do with the water?
Leave it alone.
Leave it alone. What do we do with the carbon dioxide? Leave it alone. So then we go through and we cancel out the spectators, which in this case would be chloride ions. Anything else? No. And then of course what we're left with in this case is the net ionic equation. So this is a crash course on net ionic equations. You don't get good at this stuff without practice. And you can see, as you heard some of your peers kind of giving some wrong answers today, a lot of this comes back to your nomenclature. If you don't know your nomenclature and your ions, you're going to suffer here on your net ionic equations. All right? That's it today.